Today, the most advanced enterprise AI models in the world share a critical, fundamental limitation. They simply wait. Until a human types a prompt and hits send, millions of parameters of reasoning capability sit entirely idle. It is the equivalent of hiring a world-class domain expert, putting them on a massive retainer, and restricting them to only work when you physically walk into their office and ask a question. To achieve true operational scale, the architecture must be inverted. The system must initiate the workflow, waking up and assessing the environment without human intervention. This inversion is the core of HeartBeatAgents. The platform is built specifically to support a persistent, always-on AI workforce. The mechanism that powers this is the standing order. A standing order takes an isolated conversational agent and converts it into a proactive subagent. Every execution of a standing order deploys the platform's full reasoning engine to assess current data, utilize tools, and adapt to the specific state of the world it finds in that exact moment. To execute this safely, the platform relies on a dedicated scheduling layer, robust state management locks via Redis, and completely isolated execution threads. Migrating AI from a reactive interface tool to continuous backend infrastructure provides the operational leverage necessary for true autonomy. Scaling this architecture introduces immediate risks. If 10,000 autonomous agents are scheduled to fire simultaneously at midnight, the resulting compute surge can overwhelm databases and trigger severe race conditions. The engine regulates traffic using a 30-second Celery beat dispatch cycle that constantly queries the database cluster for any tasks due to run. Simultaneous queries from multiple dispatchers would pull the same tasks, resulting in massive, costly duplicate executions. The dispatcher prevents this by first acquiring a strict distributed batch lock through Redis, ensuring only one dispatcher operates at a time. The dispatcher evaluates current queue depth to apply back pressure if the system is overloaded, and fetches a strict maximum of 2,000 due orders per cycle. It utilizes a Redis pipeline to perform a high-speed round trip, checking the individual execution lock for every single order in the batch instantly. If an order's lock is currently held by an active worker thread, the dispatcher recognizes the task is already in progress and skips it cleanly. Implementing enterprise-grade distributed locking guarantees that the system can scale horizontally without corrupting data or duplicating automated compute. Queuing tasks safely handles execution volume, but the system also requires diverse parameters to dictate exactly when an agent should wake up. These visual nodes represent the available temporal triggers. On the clock-based side, agents can be dispatched immediately for one-off tasks, or set to an interval rhythm as frequent as every 10 seconds. For complex calendar scheduling, a time zone-aware Cron trigger allows agents to execute strictly during localized business hours or at specific weekly intervals. The asynchronous file event trigger breaks this rigid schedule to handle dynamic business operations. File events transform the platform into a reactive, event-driven processor. The exact moment a new CSV drops into a directory, the agent wakes up, ingests the data, and executes its reasoning. The platform relies on OS-native kernel notifications, utilizing systems like Linux inotify or macOS FSEvents to alert the agent only when a file system change occurs, avoiding the resource drain of continuous polling. A multiplexed file watcher manager consolidates these requests. If 500 separate standing orders monitor the same shared data folder, they share one single operating system observer to deduplicate the event traffic. Pushing event detection down to the OS kernel level prevents systemic CPU exhaustion and enables massive event-driven reactivity. Running thousands of background tasks introduces a strict resource challenge. Massive automated volumes can degrade the speed of live human-to-agent chat sessions if they share the same resources. To protect response times, HeartBeatAgents physically separates its worker pools into completely isolated Docker containers. The interactive pool consists of just 4 pre-fork processes, optimized entirely for immediate conversational human response. The standing orders container utilizes a dense 50-thread worker pool, entirely insulated from the main service. Using threads instead of processes is an intentional engineering choice. Because LLM agent execution is highly I/O-bound, the system spends most of its time waiting on external API responses, making threads highly efficient. Each thread hosts a fresh, state-aware agent invocation that loads its unique context and reasons through the specific task from scratch. The agent reviews its long-term memory to assess past states and executes a full reason-act-observe loop utilizing its complete tool registry. Isolated threaded execution ensures that massive, automated cognitive processing occurs constantly behind the scenes without blocking a human interaction. Interacting with external data and third-party APIs guarantees eventual failure states as endpoints go offline or data formats change. Failing agents can enter infinite retry loops, which would exhaust compute resources and consume API token budgets without strict safeguards. Every standing order monitors its own error history through stateful consecutive failure tracking to protect the system. An exponential backoff algorithm forces a failing agent to wait progressively longer between attempts, starting at 30 seconds and doubling up to a maximum wait time of 1 hour. If an order registers 5 consecutive failures, the automatic circuit breaker forcibly trips, pausing the order and halting execution entirely. This stateful, self-healing architecture preserves diagnostic data for recovery and physically protects the broader system from runaway cloud costs. The highest operational leverage occurs when agents programmatically manage their own temporal cadences. Agents utilize built-in tool access to dynamically create, list, pause, and delete their own standing orders. Consider a human manager providing a single high-level mandate. Keep an entire project software documentation continuously updated. The agent independently deploys a kernel-level file watcher to monitor the source code directory and instantly react to newly committed files. It then schedules its own secondary asynchronous tasks, a weekly cron order to aggregate changelogs, and a monthly cron order to regenerate internal architecture diagrams. Granting AI safe, restricted self-scheduling capabilities elevates the platform from a simple task execution engine into a self-organizing operational workforce. The HeartBeatAgents architecture replaces the fragility of standard linear automation with robust, non-deterministic reasoning applied continuously to your operations. This unified engine moves data events through varied trigger nodes, across a rigid Redis lock gate, and into the 50-thread worker pool for processing. Because this ecosystem runs completely on private enterprise infrastructure, your internal data flows, API keys, and operational schedules remain completely unobserved by third parties. Under this architecture, the agent independently initiates complex, multi-step problem-solving without requiring a human to be present. Enterprise leaders stop managing isolated, rigid workflows and begin directing autonomous outcomes, stating the goal once and letting the agents design the rhythm. This continuous cognitive execution operates invisibly in the background. It is the steady heartbeat of the system. Combining kernel-level event watching with distributed concurrency controls provides the foundational operating system required to run a proactive, self-healing AI workforce, 24 hours a day, 365 days a year.